Okay, I just want to introduce a new course I'm putting on my YouTube channel, and it is Control Systems. Control Systems. This will be an basic introductory course, Control Systems 101. I've taught this in 3 departments in 2 different universities, using at one time or another probably about 3 different textbooks. They seem to cover it about the same way. So I think this is your pretty basic Control Systems 101. Who knows if you're taking a course, if it follows the same or includes all the same subjects. I divided up into 9 modules. Here are those 9 modules. I'll talk briefly about them. First 8 are considered classic control systems, which probably they had back in the 1930s and 40s and 50s. And then this last module is state space analysis. That's considered modern analysis, even though it was like in the 1960s. Let me go through these. The first one is math models. And I taught this at 2 different universities, and both of them had a prerequisite course that covered mathematical modeling more extensively. So I'm just going to fairly briefly review a couple of simple physical systems: linear motion, exemplified by the mass spring damper system, and simple electrical circuits, resistance, inductance, and capacitance, passive RLC circuits. The big deal there is those math models, or many physical systems, can be modeled with differential equations. And that's what the rest of the course is all about. So it's going to look awful mathy. And if you wonder what's this got to do with real things, with hands-on things, here's the connection. Physical systems largely obey differential equations. We often model them that way. If you really want hands-on, that might come in a control lab course subsequent to this more mathy theoretical course. The second thing briefly introduces the Laplace transform. If you really want to know more about that, look at my NMath A course. But I'll talk about it just a little bit because it leads to this idea of the transfer function, which is a big deal in control systems. So we're going to talk a lot about that. Block diagrams, you need to know at least some block diagram manipulations. Whether you need to know signal flow graphs and Mason's rule. Mason's rule is pretty tedious. Oops. I think I just lost my Zoom again. Maybe you don't cover Mason's rule, and if you don't, you can skip this. Time domain analysis is a pretty long module. This is a big deal. We'll just get into that when we get into that. Stability is a big deal. Whether you really need to know Routh-Hurwitz criteria, I don't know. If you don't need to know it, you can skip this part of stability. But you should understand stability if you're in a control system. Root locus is a graphical technique. It goes back probably to the 1930s. It can get rather tedious. I've known a lot of students have trouble with this. Anyway, we'll get into it. It's a pretty deep, you got to spend time and do the homework problems. Frequency domain analysis. That's a big deal in control systems. And another graphical technique in the frequency domain is Bode plots, Bode graphs. So we'll get into that and how to design at least a little bit using Bode plots. Another graphical technique is Nyquist plots. So we'll talk about that. You don't really have to know that for your course. I don't know. Some of these subjects are probably skipped in some courses. And finally, state space analysis. I think you need to know at least the basics of that, even in a first course. I think the university where I most recently taught, actually second most recently taught, has skipped a lot of this first through 8 courses, 8 modules, and jump right into state space. Anyway, I'm more or less introducing state space analysis. So anyway, this will be what will be in the course. You can skip around for your needs. Some of it is kind of intense and tedious, and if you don't really need to know it, you probably want to skip it. Anyway, that's the intro to the course.